Hello, this is Brock Lemires, and in this recitation video, we are going to begin looking at mathematical operators in C. And the majority of the lessons that we're going to be going over here were developed by another professor in the electrical and computer engineering department named Dr. Ross Snyder, and he's another computer engineering faculty here at MSU. And so I put his picture there so you can kind of see who was the designer behind a lot of these figures. Okay, so what are we going to do today? Here's what we're going to do. We want to understand some of the common math operations in C. And these are everything you would think of: add, subtract, multiply, divide. And we also want to take a look at the order of precedence and how it impacts the result of an operation and how we address it when we're actually writing a program. Okay, so let's just start off and look at a simple multiplier. Okay, so here's a C program. You got pound include, standard IO, int main, we don't even know what that means yet. And then we define a double. Okay, so we put data type double, and we're actually going to define three of these. Okay, so A, B, and C. And remember what a double is. It's a 64-bit floating point number. So when you do this, it's going to allocate some space in your computer memory. And then down here, this time what we're going to do is we're actually just going to assign to A, B, and C as separate statements. Remember that you can potentially assign their initial value in the same line as when you declare the variable. But in this situation, we just declared, okay, double ABC, so that's going to allocate three locations in memory, and we don't know what's in them. Okay, then we come down here and we will assign to them. So A gets 5.5, B gets 3.3, and then we're going to do an operation. C is equal to A times B. And for now, just to pretend that you knew that the multiply was the asterisk symbol. Then what we can do is we can come along and say, let's just print out the result. So I could print out a float. Now look at, this is the double quotes, so everything in here is treated as just text unless it's preceded by the percent. So when I say percent 2.1f, what that means is that it's going to print a float. It's going to print the value of a float, and it's going to say, you know what, only put a maximum of 2 leading digits before the decimal point and a maximum of 1 trailing digit after the decimal point. So that's what the syntax is. Okay, and then I'm going to put times, and remember that it's just going to print the ASCII character, the actual symbol for the asterisk, because you're within the double parentheses. And then it's going to do the same thing. It's going to print another float with a maximum of 2 leading digits to the left of the decimal, 1 trailing digit to the right. And then it's going to type equal. And remember, the equal in this situation is a printf equal. It is just the symbol for equal. And then it's going to print a final float, or a final double in a floating point format. And it's going to allow up to 4 leading digits to the left of the decimal and 2 to the right. And then we say, okay, so you got these placeholders in your print statement for where variable values can go. What variables? So after you close up the double quotes, you put a parenthesis or a comma, and then you type A, comma B, comma C, and that assigns A will be printed here, B will be printed here, C will be printed here. Okay, so this is a review of stuff that we've done already. The output of this program will actually print 5.5 asterisk 3.3 equals 18.25. A couple things to note. Okay, notice that 18.15, the leading digits, the 1 and the 8, there weren't 4 of them. Okay, so we put 4 there, but that just says the max that you're going to have. Okay, so if this had come out to be like 300, it would have typed 300, and so this just sets the max of it. But this is what you would actually get on the program. Okay, and remember that this syntax 2.1 between the f and the percent, that's just going to dictate, limiting how you print it. It doesn't change the values of the doubles. It doesn't change those variable values. All it does is just how you print it. Okay, so if I didn't have those, if I just put %f, 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 it would print out a whole bunch of trailing digits. Okay, so it's it's pretty relatively straightforward. But why don't we take a look at more details of what is going on in a computer system? Okay, to understand a computer architecture in detail, to be able to actually design it from scratch, it takes many years. It takes many times coming back to the material. But this will be, let's just pretend this is the first time you've ever even heard some of these terms. This will be kind of your first exposure to what a computer looks like. So within a basic computer, we've talked about this concept of memory, okay? And every computer has memory, okay? Memory is storage, all right? And the way that computer memory works is you have memory content, which is where you can store information. But each of these locations in memory is assigned an address. It's assigned a unique address. And that's because you want to be able to go to any one of these locations and either put information there or get information. Okay, and so we need a unique address to basically facilitate how or the locations in memory that you're accessing. Okay, so typically when you draw out memory, you draw it just like this. It's all these little boxes that you can put information in, but then it always has this memory address over here. Okay, now what's beautiful about a higher level programming language such as C is it kind of hides what's going on in terms of the memory access. You don't have to actually know the exact address of memory when you define a variable. So when you say double A and you define this variable that's of type double and give it a name A, it's going to go somewhere in memory. Okay, but you don't have to go out and say put it at address location 2. Okay, the operating system of your computer handles that. The operating system manages where programs are getting access to memory, so you actually don't ever have to worry about that. And that's a good thing too, because keeping track of all those addresses can be kind of difficult. But anyway, that's just memory. Okay, you've probably heard this called like RAM, or you've probably heard of like your DRAM on your computer. That's what they're talking about. They're talking about this memory right out here. The brains, though, of the computer is called the CPU, and that stands for Central Processing Unit. And this is a very simplified model of what's going on, but basically this is where all the circuitry is to perform operations and execute your program. Okay, so within the CPU, there are these things called registers, and you can think of these as just really fast storage. Okay, so much faster than memory. Okay, memory might take a little, a certain amount of time to access. Registers are just instantaneously. It's just like boom, boom, boom. You can get information into them and out of them very quickly. They're also very important because there's another component within the central processing unit called the ALU, and that's called an arithmetic logic unit. And this you can think of as the circuitry that performs math operations. Okay, so this is, if you were going to add two numbers together, there's a circuit in your CPU that knows how to add. If you're going to multiply two numbers, there's a circuit in the ALU that's going to multiply the numbers. Okay, but where does the input of the ALU come from? Well, it actually comes from the registers, because you want to be able to have a fast storage device that'll hold the information you're going to operate on, feed it into the ALU, and then the result of the ALU goes back to another register, because this happens really, really quick. So the CPU contains these registers, and it contains the ALU, and it also contains the brains of how to go out and read your instructions that are your program and execute them. Okay. Then of course in any basic personal computer, Mac, you have an input and output. Okay, so that's also important too, because without input and output, you just have a computer that we don't know what it's doing, right? So the computers are here to serve mankind, so we need a way for mankind to enter information. So input might be a keyboard or mouse, like you would suspect. Output is the most common, is the monitor. It could be a printer though too. Okay, so that's kind of a general purpose, just architecture. Okay, like I say, if it's the first time you've ever heard that, that's fine. It takes many touches on computer architecture to get a feel for what's going on. So let's take a look at how that program that we just executed would look when I look at that kind of block diagram of a computer. So I come into my program and I see int main. We have no idea what this means. We're just typing it every time we type. We'll probably get to that potentially in a couple recitations, but we just know we start our program like that. Okay. Well, this one though, we kind of do know what's going on. When we get to this line that says double ABC, we know that we are defining three variables that are of type double. Okay, so we want to create these variables, and we want them to store information as a 64-bit floating point number. And that's good, because we can actually store and represent real numbers. So we can have decimal points in there, 3.1415, etc., etc. Okay, and we're going to do three of them. But we know that those variables are going to be stored in memory. So what we're actually doing is we're allocating memory out here, memory locations. So for example, this is an example of, assume that A, this guy that we defined right here, happened to be put in memory right here at an address that was in hexadecimal 0100. Okay, you don't even have to know what hex is. It's just a way of representing numbers. But let's just say, for example, it was at 100. B was at 1FE2, another address, and then C was somewhere else. Now you go, geez, man, these are all over the place. Why are they all spread out? You don't have control over it, to be honest with you. It's the operating system that handles it. So when you write this program, what you're doing is you're saying, I'm going to write a program that's going to request from the operating system, hey, I need 3 locations in memory. It needs to be at least 64 bits. Can you help me out? The operating system says, you know what, I can do that for you. I'm going to give you this fella up here, we'll call it A, this guy called B, this guy called C. So you now have that information, okay? So it's like, okay, now what happens when we go to the next lines of our C program? Well, when I do this, A gets 5.5 and B gets 3.3. What you're doing is you're initializing those locations in memory. So these are written in decimal. We kind of know that in memory it's all stored as ones and zeros. But for this example, you can kind of think about those ones and zeros are representing 5.5 in a floating point format. So when I execute A is equal to 5.5, I go out to memory and I initialize it to 5.5. Now you might say, who's initializing it? This fellow over here. CPU? The CPU is reading these instructions that result from compiling this program and saying, I can do this. Okay, I'm going to go out here and I'm going to put 5.5 in there for you. I'm going to put 3.3 in here for you. Life is good. Then you go to the next step, which is going to be multiplying. Okay, so now you go, okay, what in the world is going to happen here? Well, remember, this is just storage out here. Memory is just storage. You need to bring these values that are the inputs to your multiplication operation into the CPU, and you need to hold them in registers, and then you need to use the ALU to perform the multiplication, store it back into a register, and then store it back to memory. Okay, so let's take a look at doing this. Okay, what is written right here is a little bit more detail in terms of the instructions that are executed to execute this program. We are using C. Okay, C is a high-level abstract language that allows you to do things where you don't have to have intimate details of the hardware. Okay, and what this is showing, this is actually, it's called assembly language, but it's interesting because each line in this assembly language, code actually represents an individual instruction that the computer executes. Okay, because we talked about before where you write a C program, you make it or compile it, and then the instructions are created as ones and zeros that can be executed by the computer. Well, this is a way to kind of just represent those individual instructions, but kind of give it more readable names just so we can understand it. And it turns out this is called assembly language, but it just illustrates how it's very simple instructions that are executed very rapidly. So the whole notion of here we're going to do a multiply, the CPU is going to say, let's go, guys. You guys need to come on over into some of my registers. So it's going to bring 5.5 and stick it in one of its registers. It's going to take 3.3 and put it into one of its registers. Then it's going to turn on the ALU and say, ALU, go ahead and crank out a multiplication. And when your result comes out, throw it back into one of the registers. Okay? And that is essentially one instruction that the computer executes. So it had to bring those puppies over, it had to do the multiplication, and now you're going, well, okay, so I got 18.15, where do I put it? Well, the last thing that the program will do is it will take the result of it, which was held in a CPU register, and it'll put it back into the memory at the address that was allocated for the label or variable name C. Okay, so it's like, oh, this is pretty sweet. Now, like I say, this is way more detail than what you need to know to write a C program that does this right now, but it's good to start just being exposed to what's going on underneath the hood of the computer that you're programming. Okay, and you'll touch this many times as you develop your programming skills and learn more about computer hardware. Okay, so feeling good about hardware, let's take a look at the arithmetic operators that are available for you in C. The first one is called assignment, okay, and we've already used it, but it's where you use the equal sign. What's important about the assignment operator is that whatever you're assigning to has to be on the left. So in this situation, you'd say A is equal to B. What that means is that the variable A will get assigned whatever was in B. That's very important to know that A is what the destination is, because you could look at this and go, well, maybe B will get what A is, or maybe A will get what B is. It's like, no. B had a value. When this instruction's done, A is going to have that same value because A was on the left. Okay, addition, the operator is a plus sign, shocking. Subtraction is a subtract sign, shocking. Multiplication, it's actually asterisk. You could go, what about x? It's like, no, it's not x. It's asterisk. Division is the little fractional point, the forward slash. That kind of looks forward. Modulo, you probably never even heard of that one, but what this is where you do, it gives you the remainder of a division, so it's kind of like it uses the same forward slash as a division, but it puts these little circles around the forward slash. That's called a percentage sign. Now, that's just an operator just to kind of show you that there's other operators in here. Probably not going to use modulo very much in this example. Then we have increments, and what increment does is you can, instead of saying like A equals A plus 1, that would increment A. Okay. You can also do a shortcut where you just say A plus plus. Okay. And you can put plus plus A or A plus plus, and what it means is that it depends on when you're going to increment A. So if you do a plus plus A, what it'll do is it will increment prior to the assignment, whereas if you do A plus plus, it'll increment after the assignment. Okay, and it's a really subtle difference, but it just shows you that you can either make the assignment then increment, or you can increment your variable then make the assignment. Okay, same thing with decrement. Okay, so that's pretty neat. Let's take a look at an example of doing some math where it's more than just A times B. Okay, so I come along and I say, what does D equal? Well, now we got a little code snippet here, and we got double A, B, C, and D. So we've created 3 of these things. We've initialized A, B, and C as 3, 4, and 5. Totally acceptable. We know that these are doubles, and even though we didn't put fractional or decimal point and fractional numbers on here, that's fine. It's going to read these as 3.0000 and 4.000. Okay, so then we get down here and we're like, D is equal to A plus B times C. All right. Well, wait a minute. Let's think about this. Is this answer going to be 3 plus 4 times 5, where you perform 3 plus 4 first? So that would result in, okay, I'd have 3 plus 4 is 7, then I multiply it by 5, that would be, the answer would be 35. So that's kind of like, does it execute as if it goes left to right? I don't know, maybe, I don't know. Or is it, do you do the multiplication first, where you would take 4 times 5 and equal 20, and then add 3 and get 23? So it's like, oh, geez, this is horrible. Well, it turns out, just as in algebra, okay, there is an order of precedence, and that means that some operations have higher priority than other operations. And this is a table that shows you the order of operation. And before I look at that, if we think about algebra, if you go back to this, which one of these would execute first if you wrote this out and solved it by hand? Well, the answer is, multiplication comes before addition. So if you did this by hand, you would take B times C and you would add it to A, because those are the rules of our manual algebra. Well, it turns out that many of those rules are also followed in the programming language, except that there's just a ton more. Okay, so the highest operation possible is the parentheses. Okay, so the parentheses is the granddaddy. All right, if you put parentheses in there, anything within that parentheses is going to execute first. Okay, now there's some other things that we haven't even covered, like typecasting and one's complement. It's like, all right, well, it's good to know that there's operations that we don't know of. Here, there's size of. That's one we've seen before. Okay, but let's go down here. Notice here's multiplicative, and that is your multiply, divide, and modulo. Okay, so those puppies right there are going to have higher precedence than additive. Okay, and additive means plus and subtract. Okay, so that's right there. Those are the rules of engagement for if we actually executed that program, it would look like this. Okay, so it would say, all right, I know that multiplication has a higher order of precedence than addition, so it will automatically do 4 times 5 first, and then it will give you the result. But here's what's interesting. You hear that for the first time, you're like, wait a minute, what if I have, you got like plus and minus on the same line here, and you got star and forward slash and parentheses on the same line? Who's higher priority amongst these three? Well, the way that you read it is it's left to right. Okay, so if you didn't put parentheses and explicitly tell what operation should go first, you would go from left to right in the expression. Okay, and what I mean by that is if you came back to this guy and you said, pretend that this was A times B times C, it would go left to right. It would do the leftmost multiplication, then the rightmost multiplication. Okay, so that's how you handle that. Okay, let me tell you a little secret here. Don't even try to keep track of order of precedence. Always use parentheses. Okay, it's good to know that it has rules for this, but you want to use parentheses for everything. This is the exact, or this is not the exact same thing. If I put parentheses in here, this would be how I override the order of precedence and say, I'm going to take A plus B first, then I shall multiply by C. But what I like to do is I always put parentheses around everything. Okay, so this feels pretty good. I mean, it's like we're looking at these operators. How about we do some of these? Okay, let's do an example together where we do something interesting. Okay, so we're kind of learning about electricity, and we've heard of things like current and power, voltages and resistances. Even if you haven't, it doesn't matter, because we have equations that we're going to implement here. But let's take a look at this circuit. This is a circuit where you have a voltage source and the value of it is V. We'll call that's our variable name, and there's a resistor over here, okay, and that's the squiggly line, and it has a variable name of R. And when you put these together, what happens is current will flow, okay, and the current, we'll call it a capital I. And the equation that governs how much current will flow is Ohm's law. And it turns out that if you're solving for I, you can find I by taking the voltage and dividing by the resistance. So it's a very simple equation. You can also find the power dissipated in that resistor, or in the voltage supplied, or power provided by the voltage source and dissipated in the resistor. They're the same, by taking the current and multiplying it by the voltage. Okay, so we want to write a program that will do that. Here is how we'll do it. Let's prompt the user for the voltage. So we'll say, what is the voltage? And they'll give it the voltage. Prompt the user for the resistance. We'll get the resistance. Calculate the current, calculate the power. You calculate the current first because you actually need to know it to calculate the power. So we have to do that one first, that one second. And then let's print out the voltage, resistance, current, and power, okay, including units. That'd be handy. Now, based upon what we've learned so far, we need to keep in mind a few things. First, when we prompt the user to type something from the keyboard, it comes in as a string. Okay, so it's not a number. If they type 15, it's not going to come in as a double with a value of 15. It's going to come in as 2 ASCII characters, and you'll have one 8-bit code to represent the symbol 1 and one 8-bit code to represent the symbol 5. So to get around that, when you're trying to get information such as numbers from a keyboard, you have to convert the strings that come in to actual numbers. So what we'll first need to do is we'll need to create variables that will hold the string inputs for voltage and resistance. Then we'll create 2 variables of type double that will hold the floating point or the real values of those after a conversion, and then we'll convert those strings to their actual values. Then we can perform the multiplication. Okay, so let's fire this up. Okay, so I'm going to launch my putty. So here is my putty right here. And I'll load in my server that I had saved before, and I'll say open. Okay, so here comes my console. I'm going to log in as my username, usernet ID, get a password, and let's take a look. Present working directory. I'm in here, LL. I've got my 2 recitation folders. Let's go ahead and make a directory by going mkdir rec3, and this is where we'll put our program. Okay. All right, so I take an LL and look, and I've made a folder. Let's change into rec3, and what's in it? Nothing, as you would suspect. Okay, this is great. So let's call our program file RCA or R3A .c. Okay, so I'm going to go Emacs R3A.c, and that stands for Recitation 3 Assignment. Okay, so go ahead and fire up Emacs, and there's nothing in it. I haven't even created the file yet. All I'm doing now is I'm just starting to edit. So let's go ahead and enter something, pound include, and we always want to get our standard io.h library in there because we'll be using that to read from the keyboard. And let's go down here and we'll do int main. We have no idea what that means. We do know that if we open curly brackets, all of our statements should go within the curly brackets, and then whatever, it will execute whatever's in here. Okay, and then we'll do return 0. At this point, again, we don't know what any of this stuff is, other than including the standard I/O. Okay, so at this point, let me save it. I'm going to go ahead and go Control X, Control S for save, and I should have created this. It says wrote r3a.c. Let's fire up another putty SSH shell. And the reason I want to do this, I want to see the file going, and I want to kind of compile as I go so I don't make too many mistakes and then have to debug them all at once. So I get another console going here, another terminal, and I take a look at where I am, and I'm at my home directory, ll, rec3, cd, change directories into rec3, and let's check out what's there. r3a.c. Perfect. Okay, so I have my little fella there, and now I'm ready to keep rolling here. And let's see, where did my other putty go? So here's my other putty. All right, so now I'm sitting here and I'm ready to start cranking this stuff up. Okay, so let's think about what we need to do. The first thing we need to do is we're going to grab the voltage from the user, and we are going to bring it in as a string. So the first thing that we need is a string variable. Now remember that a string is just a one-dimensional array or vector of type char. Okay, so the way that you do that is just say char, and then I give it the string a name. So I'm actually going to call it vstr for string, and I give it these square brackets, and then inside of this, these squares, I tell it the size of the array that I want, or of the vector. Let's go ahead and say 100. Okay, so it's going to have it can accommodate 100 keystrokes from the keyboard. Now that's insane. I mean, unless someone wants to enter like 9 bajillion volts, we won't need that many, but it's like, okay, 100's big enough. It should handle most of what we're going to do. I go ahead and change that. While we're here, let's go ahead and do our resistor string, okay, because we're going to ask for the value of the resistor. We'll make it the same size, okay, and now we're going to ask for the value of the voltage, okay, and what I'm going to do is I'm going to kind of create the variables as I need them, and then just kind of the way that I think through it. Okay, so let's think about this. I'm going to go print f, and I'm going to say enter the voltage, okay, and that's all I'm doing. And now the user is going to type to me a number, okay, on the keyboard. Okay, and it's like, okay, well, they're going to 12 volts, 5 volts, whatever. I need to do an f gets, okay, and then what I'm going to do is I want to put this information that's typed in the string vstring, and I need to know the size of vstring, so I can type 100 even though I know it, or I could do the function size of. I always like to use size of because it automatically does it, so I don't have to worry about it. And then you get the information from standard in. Okay, I've brought in the voltage, but the voltage is now entered as a string of characters. Okay, so if the user typed 12, it's not going to be a floating point or a double of a value of 12. It's going to be the ASCII symbol for 1 and then the ASCII symbol for 2. Okay, so what we immediately have to do is we want to take those strings and we want to convert them over to a floating point or a double format. So if you remember how you do that, you actually come in here and you do these conversions where you say the function name is actually this one. It's ASCII to F, and then what you give it is the string. So if I do this right here, it's going to take whatever the string is, v string, and it's going to convert it to floating point format, but the result is a double. Okay, so what I want to do is I need to put right here what the assignment is going to be. So once I convert it to a double, where is it going to go? Okay, so let's come up here, and now what I need to do is I need to define a new variable called double, or of type double, that has some name. So let's call this v, and let's just call it dBl for double. Okay, and that is going to hold the floating point version of the voltage that the user entered. Okay, so it's like, all right, while I'm here, I might as well do a R double. So R double. Okay, and you can name these whatever you want as long as it makes sense. But okay, so I come along here, and I want to do V double, and now I've converted it to there. So what I would like to do is let's print out down here what we just got, and then let's make this and make sure that we're okay. So I'm going to say print F, and I'm going to say the voltage entered was blank. And now I'm going to go %F, and I'm going to that's going to insert the value of the variable that I type right here, which is V double. Okay, now notice that I put a line return, then I closed my double quotes, and then I said V double. Okay, so at this point, let's think about if we've got everything right. Okay, we had the standard I/O, which allowed us to do the fgets. What we didn't include was the ATOF. Okay, so that function is actually in the standard lib, I believe, and we can actually check it if we went out to our manual, but I'll just tell you it is because I just looked it up. Okay, so I'm going to do pound include, and this one's going to be standard lib.h, and now that gives me the function ATOF. Okay, let's try this. Control X, Control S. I wrote it. Now I come out here, and I'm going to say make R3A. Let's see what happens. Okay. All right. Now we have an error. This is interesting. So let's take a look at what is going on here. We have in function main warning, unknown escape character. Okay. So you look at this and you go, where did I screw up? Oh, it's telling me line 14. So I come down here, and you can turn the line numbers on in Emacs. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Somewhere on here, there's a problem. Oh, look at this. I put a space between the backslash and n. Okay, no problem. I'll fix that up. Control X, Control S, and make it again. Boom. It worked. This is why we compile often. Okay, you don't like to save up all these rinky-dink errors for the very end, and then you have to debug like 20 things at once. It's better just to compile as you go. So let's go ahead and run this. I'm going to go R3A. So I go ./R3A, and I run it. Enter the voltage. Let's say 14. The voltage entered was 14. Beautiful. It worked. It worked. Okay. You know what else I'd like to do? I'd like to go ahead and limit this because I want to put some units on here. So instead of having like 1,000,000 decimal points, let's go ahead and make it like a 2.2. And then after the number, let's put its units. Okay. So I'm going to put in parentheses now. Actually, I'll just put volts. Volts. So let's go Control X, Control S, and then let's do this. Make it, run it, enter the voltage, 12. Beautiful. It says the voltage entered was 12 volts. Okay, I got it. This is cool because now I can actually just kind of copy and paste this. Now, there are copy and paste commands in Emacs, but it's probably funner for you to watch me type it. So now let's enter the code to get the resistance. Okay, so I'm going to go print F, and I'm going to say enter the resistance, and then I'm going to do colon, space, line return, and then close it up. Boom. I'm going to do an fgets, and I'm going to put this in this variable I created called rstring, and it's going to be of size. I'll use the function size of rstring, and then I'll get it from standard in, which is the keyboard, and now I have it as a string. But what I really want is I want to convert it to a double. So I'm going to say r double, the variable I created up top, is equal to, and I'm going to use the conversion function ASCII to float, and I'm going to enter the string I want to convert. That's r string. Okay. All right, so this is pretty good. One thing I don't like is how everything's green. Notice how that, it's like, God, man, why is everything green? I must have forgotten something. Well, this guy over here is red, this first double quote. It almost has acting like I don't have the second double quote. Wow, isn't that cool how Emacs will color code for you? It reminded me pre-compile that I actually need another double quote. Okay, life is good. Let's test this. Control X, Control S. I'm going to go ahead and say make it, run it. Voltage, let's go 11. Enter the resistance, go 50. Okay, so we got 50. Oh, guess what? Forgot to print it. Let's come here and go print F. The resistance entered was, and then I'll go parentheses 2.2, and then I'll say float, and then I'll say ohms, and then I'll print our double. And then I'll close that up. Okay, feeling good. Control X, Control S. Come over here, make it, run it. Voltage was 13 this time. Resistance was 44. And now the voltage entered was 13. The resistance entered was 44 ohms. Fantastic. I'm now ready to actually implement the operators, the whole point of this this video. So let's take a look at what we need to do. First of all, we are going to simply find the current by taking the voltage and dividing it by the resistance. All right, we can do that. We need a storage location for the current, so let's go up here. And now let's think about something. Should the current be a string or should it be a double? Well, you know what? It's a double because it's going to be a number, and we already have the input arguments to the division as doubles, so we're set. The user is not entering this as a string. So I'm going to say I double, and I come down here, and I'm going to do a calculation. Okay, I'm going to say this. I double equals, that's the assignment operator, and it's going to be V double divided by R double. Boom. Okay, let me check that equation. Looks good to me. I double gets V double divided by R. Okay, now guess what else we're going to do? Let's go ahead and do the power right now. So now that I have the current calculated, I need my power, so I need to make another one, so I'll call it another variable. We'll go P double, and then we'll come down here, and let's do that calculation. So I'm going to go P double gets equal to I double times V double. Okay, now here we go. I can now check, and you know, and as long as the statement is listed above this statement, you can think of it as these statements are executed in the order they appear. Okay, print F. I'm almost done. The current in the circuit is, and now I'm going to enter my float. Let's give it a 2.2 F, and I'm going to give it its units. Remember, the units of current is amps. And then we'll go return, and then I'm going to print out I double, and then I close it. And why not do power at once too? So now let's go the power in the, let's see, the current in the circuit is, that's true statement. The power, let's see, dissipated in the resistor is, and now we'll do 2.2 F, and then the unit is watts, and then I'll go line return, and then I'm going to print P double. Okay. The only thing I don't like is this puppy up here. I got the lowercase v on there. All right, I like this. I'm kind of liking this. Let's go ahead and Control X, Control S, and then let's bring up our other guy. Let's make it. Ooh, we got a, did I misspell double? DLB. That ain't gonna work. Let's go over here. Where is it? Right there. D double. Okay. Control X, Control S. Make it. Oh, geez. I ran it. Sorry. Make it. Run it. Here we go. 10 volts. Just random. Resistance. Let's make it 50. Look at this. The voltage entered was 10. The resistance entered was 50. The current in the circuit is 0.2 amps, which 10 divided by 50 is indeed 0.2. And the power was 2 watts. So 0.2 times 10 is indeed 2 watts. We did it! Okay, we did it. We have created a program which does some calculation of some electrical quantity that we needed. Okay, so we don't have to actually do this by hand anymore. We can write a computer program to do it. So this is unbelievable, okay? And so you're sitting there going, we did it. So now what do I do? Well, first, what we want to do now is let's just take a minute and look at how happy you made me. You're typing along. I mean, my head could probably not even take a bigger grin than this. I mean, it's almost touching my ear. Borderline creepy, not going to lie. Probably not as creepy as somebody taking a picture and then cropping it into here. I don't know who did that. But anyway, but I think that it's more than just what you've done here is you've done a whole lot of user input. You're making doubles, you're making strings, you're doing conversions. It's a whole lot of things are going on, and that's even more worthy of something more like this. Boom, thumbs up. Okay, you did it. You got a thumbs up there. Let's go back to the creepy though, and let's think about this. At this moment, you are going to go take the Recitation 3 quiz in Brightspace, okay? Then you're going to go to your Recitation section, work on your program, and demo it to the instructor. Your program will be highly similar to what we did here. It's going to be getting information from the user and performing some operations, some math operations in order to produce results. The equations will be given to you, but they're not the exact same one that we did here. After you demo that, you're going to upload your R3A.c file to the rec number 3 code upload. So you'll have to go ahead and FTP it back, and then you are done. So nice job and good luck.